Okay, this is a second video on stationary points, just because there is one more method to be able to find them and to find the nature of them that I think is worth discussing. And that is a method using second derivatives. So if you haven't seen my last video on what stationary points are, or the basic way of being able to find the nature of them, go back and watch that quickly, because otherwise a lot of what I'm saying is not going to make sense. So we are going to be relating this idea of stationary points to this idea of second derivatives, d2y over dx squared. And if you remember from my video on second derivatives, again, entire video out about that, then we discussed how this here discusses how a gradient changes. A gradient discusses how a function changes. So a second derivative is a gradient of a gradient. It discusses how a gradient changes. So if I have a curve like this, my gradient starts off pretty sharp and pretty negative, say -10, and it slowly becomes shallower and shallower and shallower until it kind of looks like it's almost a straight line with no gradient. And our second derivative tells me how this exactly changes. How quickly does it go from -10 to 0, etc. So how does this help us with stationary points? Well, let's sketch out a maximum point. So here's my maximum point. Now let's zoom in. What is happening to the gradients just before and just after? And remember, this was the whole concept of what we were doing in the last video with calculating the gradient before and after. But what's happening to it? Well, here, my gradient is positive, right? We're going up. And it's slowly getting shallower. It looks like that, right? If I zoom in. The gradient is slowly getting shallower. The gradient starts to decrease until it hits 0. Stationary point has 0 gradient, remember? So it's going to hit 0. And then after that, it starts increasing negatively, right? So we decrease positively, hit 0, and then it starts increasing negatively over here. So again, it might start at -10, -5, 0, 10, 5, 0, and then -5, -10. So why is this relevant? Well, going from 10 to -10, or 5 to -5, means that my gradient is decreasing. My gradient is getting smaller and smaller and smaller. So the rate of change of my gradients is negative because it is getting smaller. My d2y, my dx squared, is less than 0. So if I have a function and I solve it, for d2y dx squared, and I get a negative value, without messing around with a point on either side and differentiating it like that, we can prove that it has got a maximum point. Similarly, for a minimum. At a minimum point, my gradient is starting off negative, say -10, and it is slowly increasing until it hits 0, and then afterwards it is increasing and increasing again. So the rate of change of my gradient, my d2y by dx squared, is greater than 0. It is increasing. It's going from a minus value to a positive value, which means the number is getting bigger. So d2y by dx squared is greater than 0. So if I just find my d2y dx squared of a function, throw in the coordinate of the stationary point, I can check if it is less than 0 or greater than 0, and hence if it is a minimum or maximum point. Now, what if it equals 0? Well, if it equals 0, that means there's no change of gradient. But that doesn't really tell us much, because, I could have something that looks like this. That's a maximum point, but it's got no change of gradient going on over here. So if it equals 0, so if it equals 0, then this whole method is no good, okay? If it equals 0 after our calculations and we've double, triple checked that it equals 0, we need to go back to the last method, which is why I taught you that first, because it is sometimes necessary. This is quicker and it works a lot of the time, but sometimes it just fails. And if we end up with something that equals 0 at the end, then we need to go back to the original method. So, first two things I'm going to do if I'm discussing stationary points is dy by dx, find the gradient and equate it to 0. So, dy by dx is going to be 6x squared minus 30x plus 24. That's my gradient. And at a stationary point, this gradient is going to equal to 0. Now, if I solve this using a quadratic formula or factorizing, I will save some time and say that this has values of x equals 4 and x equals 1. Okay, so here are my two coordinates of my stationary points. There is a stationary point on this curve when x equals 4, and there's a stationary point when x equals 1. So to determine if these are maximum, minimum, or points of inflection, I could, take the 4, take 3.9 and 4.1 and put it back into this equation and see if it's positive or negative, and then draw my little diagram, all the good stuff from last video. Or I can apply my new idea, which is, let's get some d2y by dx squared. So let's calculate it first. So let's differentiate our derivative again. So I end up with 12x minus 30. Now remember, we are putting in our x coordinates into this equation, into the change of the gradient, okay? The rate of change of the gradient, this function here. We are then looking to see if it's greater than 0, in which case it is a minimum, if it is less than 0, in which case it is a maximum, or if it is equal to 0, in which case, unfortunately, I'm going to have to go back and do my 3.9 and 4.1 method with all this nonsense, but hopefully we'll be okay. So d2y by dx squared, 12x squared minus 30. So 4x equals 4. I get 12 times 4 is 48 minus 30 is 18. And 18 is greater than 0. So at x equals 4, my point is a minimum. And then at x equals 1, well, if I put 1 into this equation, I get 12 minus 30, which is minus 18, which is less than 0. Therefore, I have a maximum. And obviously, this is a lot faster than the original method we described and is a lot simpler.